Large language models have achieved remarkable progress across natural language tasks. But beneath the surface, they often exhibit troubling behaviors: unfairness, inconsistent responses, amplification of harmful content, and the reemergence of biased patterns, especially during long, multi-turn conversations. These issues aren't just surface-level quirks. They stem from internal representations that accumulate bias over time, driven by dialogue history, context, and memory. Once a model starts down a biased path, it can reinforce itself, repeating stereotypes, drifting from factual accuracy, or producing toxic outputs without clear intervention. Traditional solutions rely on training time fixes, fine-tuning, reinforcement learning from human feedback, or data filtering. These methods work, but they're expensive, irreversible, and rigid. They require full retraining and can't adapt once deployed. Worse, they treat bias as a static property of a model, not a dynamic process shaped by conversation. In contrast, inference-time methods offer lightweight, reversible alternatives: prompt engineering, logic reweighting, vector steering. But most of these are shallow, static, or designed for single-turn use. They fail to capture the evolving nature of bias across multiple turns. Enter our solution: Dynamic Neuron Suppression, a new framework for inference-time fairness in conversational LLMs. Unlike static pruning or one-off interventions, our approach detects bias as it emerges, identifies the neurons responsible, and applies adaptive, reversible masking during generation, without retraining, without permanent damage. Here's how it works. First, behavioral detection. We monitor model outputs in real time using a combination of LLM-based evaluators, GPT-3.5 Turbo as the primary judge, Claude as a secondary validator. We compute a turn-level bias score, measuring how harmful or stereotypical the response is. This gives us a clear signal when bias appears. Next, bias neuron identification. We use integrated gradients to trace back which neurons in the model's hidden layers are most responsible for that biased output. But here's the key innovation. We decompose neuron importance into two components: local relevance, how much a neuron contributes in the current turn, and carryover influence, how much it persists from earlier turns. This allows us to distinguish between transient activations and those that are actively propagating bias through the conversation. Then, aggregation and ranking. We pool these scores across tokens, instances, and paraphrased instructions, using weighted aggregation to emphasize high confidence, context-aware signals. This gives us a robust, history-aware ranking of bias-carrying neurons. Now comes the critical step: concept-based testing. Not all high-impact neurons are bad. Some may be responding to legitimate context. So we run a memory consistency probe, a contrastive test that asks, does this neuron still remember the biased concept when the conversation shifts? If the neuron persists in activating even when the context changes, it's likely storing a harmful association. If it forgets, it's probably just a one-off response. Only then do we apply dynamic neuron masking. Instead of permanently pruning neurons, like cutting a wire, we apply a gating mechanism that temporarily suppresses their influence during decoding. The gate is adaptive. It's controlled by a sigmoid function that combines two signals: current bias score and memory consistency. So if the model starts drifting toward a stereotype, the gate tightens. If the bias is transient or contextually justified, the gate stays open. And because we're not deleting neurons, just modulating their output, everything can be restored. The model regains full capacity when the bias is gone. It's reversible, lightweight, and runs entirely at inference time. We evaluated this framework on two benchmarks: PCT, Political Compass Test, a multilingual dataset with 62 ideological statements translated into English, Urdu, Punjabi, Sindhi, Pashto, and Balochi. FairMT-Bench, a large-scale multi-turn dialogue benchmark with 10,000 conversations across 6 fairness-critical tasks, like anaphora, ellipsis, inference misinformation, and jailbreak prompts. The results are striking. In single-turn settings, our method reduces bias scores by over 60% compared to baseline models like Mistral and DeepSeek, performing prompt engineering, output filtering, steering vectors, and even static neuron pruning. And in multi-turn conversations, the improvement is even more dramatic. Look at Figure 4. Without mitigation, bias scores climb steadily across turns. But with our dynamic masking, the curve flattens. The model resists accumulation. It doesn't just stay fair, it remains coherent. We also measured downstream quality: fluency, faithfulness, relevance. And here's the surprise: we reduced bias without sacrificing performance. In fact, responses became more balanced, nuanced, and context-sensitive. Take this example. A baseline model says, women are naturally better caregivers than men. Our masked version responds, caregiving abilities vary across individuals and are shaped by personal qualities, experiences, and cultural expectations. Another, baseline, sex outside marriage is always wrong. Masked, views on sex outside marriage differ widely. Some traditions see it as immoral, while in secular societies it's often considered a personal choice. This isn't just about removing bias. It's about preserving knowledge, coherence, and fairness, all at the same time. Why does this work so well? Because we're not guessing. We're tracing the actual neural pathways of bias. Our ablation studies show that removing the memory probe leads to rebound effects. Bias returns because the model can't tell when it's still relevant. And uncontrolled masking. That causes oversuppression, shorter, vaguer, less relevant responses. But with our probe-conditioned, graded gating, we strike the perfect balance. Intervene only when needed, suppress only what's harmful, preserve everything else. This framework is also multilingual and scalable. We tested it across 6 languages, including low-resource ones like Pashto and Sindhi. The method reduces political bias across all languages, narrowing the gap between high and low-performing ones. The model behaves more consistently, no matter the language. And computationally, it's efficient. We ran everything on A100 GPUs. The overhead per token is minimal, comparable to other real-time steering methods. The entire evaluation took under 40 GPU hours. So what's next? We're not claiming perfection. Our current evaluation focuses on political bias and demographic stereotypes. Extending to broader domains, healthcare, cultural values, or legal reasoning is future work. And while the method is lightweight, scaling to massive deployments still requires optimization. Ethically, we must be cautious. Masking can't guarantee neutrality. It might suppress valid perspectives. And if used poorly, it could obscure rather than reveal bias. That's why we advocate for human-in-the-loop auditing, continuous monitoring, and culturally grounded evaluations. But the core insight is clear. Bias in LLMs isn't static, it accumulates. And fairness must be dynamic too. Our work redefines inference-time fairness. It's not about fixing the model once. It's about continuously steering it, detecting, probing, gating, while preserving the model's original capacity. We've shown that with the right tools, we can make conversational AI not just smarter, but fairer, more consistent, and more trustworthy. This isn't just a technical advance. It's a step toward